Okay, good morning, everyone. Welcome to the webinar of today. Our speaker is Dr. Saravanan Janakiram. Welcome to MS webinar. And I have pleasure to chair this webinar. I must admit it was somehow unexpected since our chair-in-chief, Maria Grazia De Angelis, had last-minute issues to be here with us. All is okay. So my personal greetings goes to Maria Grazia and to Elena Tocci. She's today in the background for the technical stuff on this webinar. It is a pleasure to have Dr. Janakiram here. He is the winner of a 2021 Patrick Mares Award, nominated in Copenhagen during Euromember Congress. It was a very tight competition, I must admit, and with many good contributions. At the end, the contribution about hybrid membranes for gas separation, a journey from lab to pre-pilot and beyond, won the competition, and by a very small extent of votes, I must admit. But I can since I can talk about personal votes, it is my pleasure to be here as a chair, and somehow it is a destiny since I was in favor of your presentation, so I can talk of myself, not from of the others. But indeed, it was a very interesting competition this year. So congratulations to you, but congratulations to all competitors of the last Patrick Mares Prize, very high level. Now, Saravanan Janakiram is a research scientist at Sintef Industry in Oslo, Norway, in the Department of Sustainable Energy Technology. He obtained his undergraduate degree in chemical engineering from Anna University in India in 2014, and dual degree masters in sustainable energy technology from KTH Royal Institute of Technology in Sweden and Aalto University in Finland, with master thesis carried out at the ETH Zurich in Switzerland in 2016. He completed his PhD in chemical engineering from the Norwegian University of Science and Technology in Norway in 2020. He has won several travel and poster awards from both European and North American membrane societies in the years 18, 19, 20. In 21, he was awarded with the Patrick Mares Award for Best PhD in Membrane Science by EMS. His field of interests include membranes, hybrid polymer inorganic non-composite structures for gas separation, including CCUS and other energy applications. And I guess that part of his interest will now be presented by himself today. So I leave the audience to Dr. Janakiram, and thank you very much.
Thank you very much for the introduction, Dr. Marco. So I'm just going to apologize first because it's 16 here in Oslo, and there's the work, there is renovation work going on here. I did not expect the sound to be continuing after 16, but I will talk as much as loud as possible so that you can hear me over the noise. I'm so sorry for this. Thanks for the introduction and this opportunity for presenting my work in the European Membrane Society webinar. And also, I would like to thank you for the vote in favor of the award, and also for the committee for nominating me for the prize. So today, I would be talking a bit more into details about the PhD work that I was doing at NTNU in collaboration with Sintef Industry. It's a bit more extended presentation of what I gave in Euromembrane in Copenhagen more elaborate and more into details of how we took a membrane which is for post-combustion capture, which is hybrid facilitator transport membranes, from the lab to pre-pilot, and then how it is going with those membranes right now. So with this, I wanted to start my presentation here. Just a second. Yeah, right. So what's the motivation behind doing this? The global CO2 emissions in the atmosphere is rapidly increasing since a century right now. And currently, the emissions have peaked up to 420 ppm. The effect of this alarming emission increase is that it is contributing to climate change. This picture is the picture of North Pole taken a decade ago. So you can see that it's very much covered in ice with permanent ice structures. But then this is a picture on the below that is taken 10 days before I defended my PhD. So that was a German expedition polar ship that went there to find that the Arctic is dying. This is clearly an effect of climate change. And climate change is mainly caused, one of the biggest reasons of climate change is the CO2 emissions in the atmosphere. And that is what we are trying to fight and bring down these technologies that is coming up. The webinar could not have been timed better. This couple of days before, IPCC released their latest report, which says that if it was decades before that we thought about climate change and stopping the climate change, then we could have gotten into solutions of natural solutions. But now there's only one choice, that we have to decarbonize our economies, and this has to be done really rapidly. So which means that in conclusion, our motivation is that we are looking for technologies that bring about urgent need of reduction of CO2 emissions from the atmosphere. So when it comes to this decarbonization strategies, one of this tried and tested strategy that works well with the decarbonization is carbon capture, utilization, and storage, abbreviated as CCUS in general. And this is basically removing carbon dioxide from large point sources, such as, for example, iron and steel industries, power sectors, which use coal and other fossil fuels, and cement industry for the manufacture of cement, and then utilize or store the carbon dioxide that has been captured. And within these 4 steps or 3 steps, which is CCS or CCUS, the capture part is currently the one which is still having challenges with respect to both techno-economics and with respect to the implementation on the strategy point of view. And with the capture part, if we are looking into more 3 technologies that comes into play when it comes to capture of CO2. One is absorption by amines, basically, adsorption by solid sorbents, and the third one, which is very much apt to our what presentation is today, that is membrane separation. Among these 3 technologies, membrane separation has considerable advantages with respect to the other, in the sense that it is high simplicity, low carbon footprint, making it one of the greenest of the most of these technologies. And it also offers high operational flexibility and modularity. If this was very good, then why didn't membrane separation kick off? That has a stall challenge that is accompanying with CO2 separation membranes. So when we talk about CO2 separation membranes, we talk about flue gas, which contains mainly nitrogen and CO2. That is on the high pressure side. And there is a membrane in between, and nitrogen is stopped while CO2 passes through the other side. So in general, this selective layer for these membranes is usually polymeric or inorganic, but given the large volumes of flue gas, it is preferred that it's polymeric membranes due to the lower cost and other advantages with respect to as against inorganic membranes. The driving force, as you know, is the partial pressure differences. But often when these membranes needs to be designed and developed in the lab and end up into a commercial production and then into an application, we need 3 of these properties to be the best as much as possible. One is that it needs to be highly permeable or high permeance membranes, which is the eventual throughput of how much CO2 can be transferred to the other side and how fast. The second one is the selectivity, which is how pure the CO2 is on the permeate side, or on the other hand, how badly the nitrogen is stopped on the retentate side. And the third one, any membrane that gives you best permeance or best selectivity should also be stable under the conditions where it is usually operated at. Flue gas, although it's relatively low temperature and low pressure, it is still subject to so many contaminants such as SOx and NOx. In all those conditions, it has to be stable. So any scientist that is working on CO2 separation membranes, typically for post-combustion capture, tries to find this, ends up in this triangle, which I call as the Bermuda Triangle of CO2 separation membranes, which is high permeability, high selectivity, and high stability. And oftentimes they end up in a situation like this, where they cannot get all the three at the same time. So why is that we cannot reach all these three at the same time? This has something to do with the traditional transport mechanism of polymeric membranes. Conventional polymeric membranes are usually transporting the gases, which is CO2 and nitrogen, on the, by a mechanism of solution and diffusion, where permeability is a function of solubility and diffusivity. And they're often limited by this very famous upper bound, which is that polymers of high permeability will have lower selectivity and the other way around. So this is something that scientists have been very familiar with, and they are trying to overcome this upper bound with a lot of strategies. One of those strategies that is used typically to overcome this upper bound is what is called facilitated transport membranes. So what is different from facilitated transport membranes with respect to solution diffusion membranes? In facilitated transport membranes, the transport of CO2 not only occurs via solution diffusion, but also occurs via a reaction pathway, basically because the polymer that is used in facilitated transport membranes contains amine groups. These amine groups reversibly react with the CO2 that is being that's in the feed side in the presence of water, and then converts into molecules that can be transported much faster, and then reversibly dissociates to form CO2 again. So you will have CO2, which has which follows an additional transport mechanism, which is a reactive transport mechanism in addition to solution diffusion, while nitrogen and, for example, methane or other components which are non-reactive or not active only follows solution diffusion mechanism. This makes a problem. This makes a biggest advantage of facilitated transport membranes, where the flux and the selectivity is simultaneously increased, trying to get us above the upper bound. So the typical polymers that is used for facilitated transport membranes are polyvinylamine, polyalamines, and polyetylenamines, for example. So why then hybrid membranes? This is another strategy that is what we thought when we wanted to design the membranes for CO2 capture and overcome the upper bound. So conventional polymeric membranes suffer this permeability and selectivity. But when you look at the inorganic membranes, on the other hand, they have performances which are better than conventional polymeric membranes, basically because they do not follow just the solution diffusion mechanism, but they follow other mechanisms which do not really are not constrained with this upper bound that we are talking about. So the idea that we include polymers plus nanofillers, which are main constituents of these inorganic membranes, to make what is called a hybrid membrane, is one of the other strategies to overcome the upper bound that we are talking about. So in this case, we basically add a polymer, and then you add nanoparticles that is arriving from an inorganic membrane, or basically nanoparticles into the polymer phase. Then you have two different phases that is being merged together. And when you obviously merge two different phases, there is an interface that is formed, and that is also something that we can play with. So basically, when you have a hybrid membrane, you have extended degrees of freedom, which is properties that are arising from polymer phase, properties that are arising from filler phase. And now that there is an interface, you also have properties that is arriving from the interface. So except when you're just choosing polymers, you tune only the polymers to overcome the upper bound. Now you have three sets of degrees of freedom with which you can play with to engineer a best performing membrane. So our idea in this PhD project was to include both these strategies together, which is facilitated transport membranes plus hybrid membranes with inorganic fillers, to form or what is called hybrid facilitated transport membranes. So we are combining the best of the two worlds to result in what we think would work for CO2 capture application. With this respect, we thought we chose two different nanofillers that we chose for testing out in this project. One was nanocellulose fibers, and the other one was graphene oxide. The rationale behind choosing those fillers is because of their dimensions, basically because at least one dimension of these two fillers is less than 100 nanometer. because when we make membranes for post-combustion capture, we know that we need very high fluxes, which means that the selective layer should be as thin as possible. So we would want at least one of these dimensions of the fillers to be less than the thickness of the selective layer that we are going to make. So that's the reason why we chose these two nanofillers for this application. So now that we have an idea in our mind that we are going to have a nanofiller combining with a polymer, which is facilitated transport polymer, and we know that we are going to apply it for post-combustion CO2 capture, that's our application. So typically, we draw a chart of how the membrane journey would look like, and then it looks something like this. You have so many milestones where you make first a self-standing film, where you form a hybrid matrix to evaluate the properties of the hybrid matrix. And then we wanted to see if this hybrid material can be coated into a flat sheet membranes on a support so that you can get the selective layer thin as possible. And we also wanted to explore if it is can be morphologically made into hollow fibers, because they have better packing density and advantages when it's respect to making modules, for example. And then eventually, when you make hollow fiber modules of very good performance, then you check if the membranes are working in a bigger scale, which is a pre-pilot scale, preferably in an industrial condition. And then with that conditions, if you think that the membrane is working, then you know the real performance of the membrane under the relevant industrial conditions. Then you get the data of the membranes validated, which you use for feasibility studies to design a pilot. And then with the pilot data, you can eventually commercialize the membrane. As you can see with the technology readiness level, the lab scale low TRL evaluation, which is present on the left side of the slide, which is up to making hollow fibers, for example. And then when you go to pre-pilot, you obviously need a lot of industrial collaboration within the project. And then when you go to the implementation side, you need a very good backup with a company of membrane producers or expertise from industries that is required for upscaling. So in this case, we are going to show you how we have done the membranes from this to on this journey and how far we went ahead with one of the membranes. Thanks to the European project, we had a very good consortium with industries on board that we were able to reach this objective. The objective of the project, which is in line with the objective of the PhD topic that I was working on, is to use nanomaterials enhanced membranes with superior permeation properties, processability, and upscaling properties to overcome limitations associated with the CO2 capture system. So in particular, as I said, we wanted to check graphene oxide and nanocellulose in facilitated transport membranes, and then make into hollow fibers and flat sheet membranes, and then try and see if they can be used in industries and do process simulations for feasibility studies. So with that in mind, we go into the first study, which is using nanocelluloses. Nanocelluloses is derived from cellulose, which is the most abundantly available polymer on Earth. And it's not new that nanocellulose can be used for this application. One of the main reasons why it can be used for this application is because of its hydrophilicity. One of the other reasons why it is used for diapers for making for children, which is cellulose, its parent. So, and hydrophilicity is very good for our application as well, because facilitated transport membranes really need water for the transport mechanism. The second thing is the tunable surface. Thanks to the hydroxyl groups present on the surface of nanocellulose, gives us immense possibilities for tuning the interface, which we said is one of the important parameters. The last one, but not the least, is the one-dimensional structure. Basically, when you have a one-dimensional structure, you can disrupt the polymer chain as much as possible so that we can load nanocellulose and disrupt the polymer chain to get the best use of nanocellulose in the polymer. Last but not the least, one of the other important reasons why we chose nanocellulose is because of its biodegradability. And given the constraints about sustainability and circularity, which is coming in the European society right now, it's one of the promising members for trying out instead of conventional polymers. So why nanocellulose directly? Because cellulose membranes have been used for gas permeation ever since. But then when nanocellulose was made into a film and we tried for gas permeation, it is usually a barrier. And the films was itself very fragile and very brittle. And nanocellulose is used in many applications as a barrier material. So what we did is that we wanted to convert this material into a CO2 permeable material. So in that regard, we tried to add something called ionic liquids. So in this case, we chose ionic liquids, which are highly CO2 soluble or high affinity towards CO2, so that we get high permeability of the CO2 in the material. So we eventually depart from a barrier property to a property where it starts permeating CO2. The added advantage when we added this material into the nanocellulose films is that the films became extremely robust with respect to mechanical properties. It was very ductile. I could easily fold the films, keep it in my pocket. Doesn't happen. Doesn't really break. Whereas when it comes to nanocellulose, it really is brittle. So where exactly does ionic liquid goes when you add it into the nanocellulose? So when you see the pictures here, you see that the nanocellulose actually likes the ionic liquid so much that it holds the ionic liquid onto its surface. So more or less like the ionic liquid, when it's added to the nanocellulose matrix, it orients itself to the surface of the cellulose fibers and stays there. So which means that these nanocellulose fibrils, because of their extreme compatibility with ionic liquids, can actually act as reservoirs for ionic liquid. So this is a STEM image with the EDX mapping, which shows that there is nanocellulose fibers here. And then you have carbon matrix, which is basically cellulose matrix. And then nitrogen, which is not present in cellulose, is seen here, which is which is also sharing the boundaries of the cellulose, which means that the ionic liquid is orienting only to the places where the nanocellulose is present. So what happens when it respect to back-gas permeation performance? Because the idea is good, we added how it actually changes the CO2. First, we looked at the water uptake capacity of nanocellulose and how it changed with respect to adding ionic liquids. We found that it increased quite a lot with respect to addition of ionic liquids. So that was a positive sign first. So then we look at the gas permeation results. Of course, we have to humidify the matrix, and we checked from a range of humidity from 30 to 90%. And we checked the CO2 permeability and the separation factor of this material. And what was interesting is that we had an increasing CO2 permeability when we increased the humidity, which is understandable. But what was more interesting is that we had a different trend with respect to selectivity, where the selectivity was increasing, peaking, and then lowering down to a value which is not still bad, but with still good CO2 nitrogen separation factor. So the increase in permeance is validated because of the effect of anion, the CO2 solubility, because basically the ionic liquids like CO2, and that now that the ionic liquids are oriented towards the surface of cellulosis, the hydrogen bonding is disrupted, and increased water uptake is also helping with the gas permeability increase of CO2. But what exactly is happening with the selectivity? So this, we tried to find out the explanation that we have three regimes of permeation. One is on the lower humidity, one is on the medium humidity, and one is on the higher humidity. Let's look at those into details. So for example, when you have crystalline nanocellulose, it's a complete barrier material. It doesn't permeate both CO2 and nitrogen. Visually represented, you can see that it doesn't really permeate anything. But then when you add ionic liquids, the ionic liquids orient towards the surface of the cellulose. That is good. But then we only have lower humidity, which means that it's not humidified completely, so that the water is not uptake. It's not in the uptake of water in the system is quite low. In this case, it still retains its gas barrier properties, where only some amount of CO2 is passing through, while the nitrogen stays while CO2 and nitrogen stays much behind and retaining its barrier property. What happens when you humidify more? When you humidify more, because of the compatibility and the hydrophilicity of both nanocellulose and ionic liquid, the chains disrupt in the sense that they become dilate to an extent where the gaps formed by the dilation mechanism only allow CO2 to pass through, but not nitrogen. That's one of the reasons why you have enormously large CO2 flux on the other side, while nitrogen is basically virtually stopped by the cellulose, which means at this condition, the nanocellulose act as a barrier to nitrogen while permeable to CO2. And in the high humidity conditions, you keep swelling it more, and the fibers dilate even more. Now the nanocellulose is just acting as a rheological enhancer, keeping the water swollen matrix intact. So in this case, you have both CO2 and nitrogen permeating quite high. That's increasing the permeability, but lowering down the selectivity. So basically, in these three regimes, you have pronounced barrier properties towards the lower humidity, and in the middle region, you selectively sieve the mechanism of sieve the CO2 based on molecular sieving mechanisms because it's only size selective. And in the higher case, it's a rheological enhancer where the dilation is no more sieving both CO2 and nitrogen with respect to the sizes of the molecule. So Where exactly did it end up in the opposite upper bound? We saw that it was quite obviously that at 60% or mid-range humidity, most of the membranes transcended the upper bound. Even at 90%, some of the membranes transcended really the upper bound. So the maximum CO2 permeability that we got is about 30%, 30 times more than the NFC pure membranes. And with respect to the long-term durability studies, we exposed this membrane to up to 30 hours without any problem, and we found that the selectivity and permeability was remaining quite stable at the conditions that we expected. So in the condition, this is a mid-range humidity conditions that we saw where the molecular sieving mechanism is quite stabilized, which means it's not an unstable system. It's a stable system when we wanted to have a molecular sieving mechanism in a membrane which is humidified. So with this, we have showed that ionic liquids can act as a softener in nanocellulose films, making it much easier to handle and also with very good permeability to CO2. On the other hand, we have demonstrated that it's one of the very few ultra-selective green membranes that uses physical sorbent ionic liquids. Why is it green? Because nanocellulose is green and ionic liquids are considered green chemicals, and we have shown that it's one of the few ultra-selective membranes which is polymeric. On the other hand, there is a gate opening mechanism where basically the nanocellulose fibrils dilate to form a gate, which is open at a mid-range humidity to only CO2, but not to nitrogen. So we have this gate opening mechanism that leads to size exclusion of gases. So when you have this membrane readily working, let's assess on the basis of what we see as a future prospect of these membranes for CO2 capture application. Yes, the membranes were quite good, the performance was quite good, but the processability, on the other hand, was very bad. The sense that the selective layer that we could make on the thin film composite membrane was still restricted to 2 micron or less. So to get into 200 nanometer, it was very difficult because nanocellulose was the only, we used nanocellulose as a polymeric material, but not any other polymer that can constitute a selective layer. So in that case, we eventually moved on to a place where we could use nanocellulose as a filler and use it to disperse into a polymer solution or a polymer matrix that you can essentially coat and reduce the thickness of the selective layer. So for that, we chose sterically hindered polyelamine, which is amines which are sterically hindered to utilize the backbone carriers effectively. And then we also use PVA as a film forming agent. For this material, we also used a mobile carrier, which is basically small molecules of CO2 that has high, small molecules which have high affinity towards CO2 that can act as mobile carrier for diffusion enhancement of CO2. So what did we actually, when we chose this polymer, we thought of distributing or dispersing nanocellulose into the membrane, into the polymer matrix, and then cast it into thin films eventually. But then we did not do it directly. We know that the interfaces play a major role. So what we wanted to do is we wanted to engineer the interface of the nanocellulose, making use of the hydroxyl groups which is present in the surface, so that we play around with the interface to get and maximize the performance that we get with introducing nanocellulose into the matrix. For that, we chose 4 different groups. One is polypropyl glycol, and the other one is PEG, which is hydrophilic, and we also chose high molecular weight PEG, which is PEG8, and we also included amino acid salt or amino acid beta-alanine functionalized into the surface of nanocellulose. For this, we used a one-step procedure where you use an EDC-NHS mechanism to couple one of the molecules, which has an N-terminated amine group, directly onto the surface, which means some of the surface hydroxyl groups are now substituted with the functional groups that we wanted to attach. So what exactly happened when we functionalized? We did not really observe any structural changes, but that was what was expected because we wanted to only attach small functional groups onto the surface. So that was quite clear that we did not really structurally affect the material and retaining its 1D characteristics. On what happened with respect to the crystallinity and water uptake. The crystallinity was in favor in the sense that when we functionalized these groups, they somehow disrupted the hydrogen bonding and it decreased the crystallinity of the pure nanocellulose matrix. That was helpful because higher lower filler crystallinity means better CO2 transport. On the other hand, what happened to water? That was also quite obvious that when we included functionalities with really likes water, hydrophilic functionalities like PEG, we ended up increasing the water uptake of the nanocellulose molecules. So for example, when it respect to carboxymethylated cellulose and MFC with PEG functionalized, we were able to increase the uptake up to 140 to 110%. So eventually, when we disperse these four materials, we try to coat them onto support. And here we were able to achieve up to 300 nanometers of selective layer, which is in line with what we wanted to have for post-combustion capture application. So what exactly was the gas permeation performance of these membranes? So disappointing from the first sight, which is that when we added nanocellulose into the polymer directly, it really decreased both the selectivity and permeability. However, the functionalities or the functionalization on the surfaces showed a promising trend. And each trend is really dependent on the properties of the material that we are going to that we have functionalized onto the surface. And we found out the MFC PEG, which is the hydrophilic PEG that is present in the surface of nanocellulose, gave the positive increase in both CO2 permeance and the selectivity simultaneously. But we want to find out why it actually had this effect, because we were originally we were planning to introduce just nanocellulose directly onto the polymer. That was eventually proved that we have played around with the dispersion stability of the nanofillers, which means that when there is no surface functionalities on the cellulose fibrils, the basic environment of the sterically hindered polyallylamine did not really help in dispersion of the celluloses. So which means the structure here that you see in AFM is nanocellulose dispersed in sterically hindered polyallylamine. You can see that the fibers are clogging to each other at a nanoscale level. But then when you functionalize this, they still retain the one-dimensional structure and distribute it evenly. And that is because of the steric hindrance or the steric stability of the nanofibers because of the PEG functional groups that we attach. And one of the reasons why these membranes perform much better than the original membranes, which doesn't have any functionalization, is because of the dispersion stability of the fillers. Now that we know that the PEG is the best functionalization, we wanted to see what happens when you load more PEG functionalized nanocellulose into the matrix. So here we have a graph of the content of PEG nanocellulose with respect to the CO2 permeance and the separation factor. As you can see, it's an increasing, it's a different trend where CO2 permeance is increased and then drops, but then the CO2 selectivity is also increasing and then dropping a bit. So what exactly is the rationale or the logical explanation behind this? That we know that increasing the filler loading will increase the polymer chain disruption, making it more easier for the small molecule diffusion. It also takes up more water, which is going to help us for facilitated transport mechanism. However, we know that when we increase the facility, the filler loading, we also decrease the amine concentration because the amines are only present in the polymer, not in the nanocellulose itself. And then you have the lower selectivity because there is higher diffusion of small molecules or molecules in general. And then you have increased chance of local defects of the densification matrix. So these are the pros and the cons. And that's exactly why we have an optimal loading where the local environment changes is versus the effect of effective exploitation of the amine groups is balanced. And that is a loading which we think is ideal for this system where we achieve a selectivity of more than 40 and then a permeance of around 650 GPU. So with this study, we found out that there was a rapid one-part functionalization with which we can functionalize cellulose surfaces with groups that we wanted to attach it to. The second is that the functional groups can actually be used as manipulating tools to control the interfaces. We found that the interface properties are very important for dispersion of nanocellulose or any nanoparticles into a polymeric system, and that can play a large role in respect to CO2 permeation and selectivity. On the other hand, we found out that the 30% loading of the best performing functionalized cellulose, which is PEG functionalized cellulose, showed an increase of CO2 permeance by up to 50% with a selectivity of 41. So when you check about the assessment of these membranes, yes, the performance was very good, and the stability of these membranes was also very good because we were able to make these membranes into 300 nanometer films, 300 nanometer selective layers, and it was performing quite well. However, we did not see the possibility and upscalability to be in a positive side. The reason is because the functionalization itself is a very expensive procedure because we want to attach PEG molecules onto cellulose. The second thing is that we are loading up to 30% of this functionalized material into the polymer, which is quite a lot of loading for achieving such a small or 50% increase with respect to CO2. So we wanted to go and diverge to our next friend that we thought we would that would help us, which is the graphene oxide fillers. So the graphene oxide, unlike nanocellulose, is a very different system where you have a 2D structure which has a high aspect ratio as opposed to 1D in nanocellulose. But the best part is that the one dimension that we see is the thickness of this graphene oxide fillers is in atomic or in nanometer range. So which gives us very much an opportunity to make thin selective layers which are very, very thin. The second biggest advantage is that due to this 2D structure and because of the carbon backbone, it has a very good mechanical strength. And we also know that the graphene oxide as such has a lot of hydroxyl groups on the surface, which makes it more hydrophilic in nature, which is very compatible with facilitated transport membranes. We did a small review where we found out the work done by so many people on graphene oxide, and we found out that when you have graphene oxide add to the system of polymers, it can basically move you in different directions with respect to this Robinson upper bound. The reason is because of the properties of both the polymer and the graphene oxide that we are adding into the system. And one general trend that we found is that when we add graphene oxide as such, they are barrier materials. So you eventually reduce the CO2 permeability. You may or may not increase the selectivity. But on the other side, if you try and make functionalized graphene oxide, or if you try and make holes in the graphene oxide, eventually making it porous, you have possibilities of increasing both CO2 permeability and selectivity. So that's one of the reasons why we chose to modify the graphene oxide that we wanted to include into the system. So we chose two different modification procedures. One is physical modification, where you have porous graphene oxide, and that is basically including large amount of unselective pores into the matrix of 2-dimension across the plane of graphene oxide. And the other one is chemical modification, where we are going to include PEG functional grooves because we found the success story from the nanocellulose, and we want to functionalize the PEG on the graphene oxide to make it more hydrophilic. So we were able to make these two nanofillers and then disperse them in the same facilitated transport matrix, which is sterically hindered polyelamine. And then we were eventually casting it into very thin selective layer on top of a porous support. And in this case, given thanks to this very thin structure of the 2D materials as such, we were able to coat ultra thin selective layer, which is less than 200 nanometers, using a scalable bar coating approach. And the other thing that we found is that the 2D materials like graphene oxides tend to align itself perpendicular or parallel in the plane of the graphene oxide is parallel to the plane of the membrane support or the selective layer. And the reason is because of the surface phenomena that we use for coating the membrane matrix. For example, when you have this, when you have a bar coating apparatus where you have a solution of graphene oxide dispersed in the polymer, and then we eventually coat it on a porous support with some pore filling agent in there. What happens is that due to the fast evaporation rate and the lowered surface energy, the 2D materials tend to align itself parallel to the surface of the porous support, which is going to help us with the gas permeation as we expect it to. And the other thing is that that's one of the reasons why we are able to make these films, make this selective layer as thin as 200 nanometers. So this mechanical force orientation, when coupled with this fast evaporation, the lowered surface energy, leads to what we call as in-plane alignment of the graphene oxide that is going to be beneficial for us to help in gas permeation. So with that, we added the graphene oxide, porous graphene oxide, and GOPEG at a very low loading of 0.28% because of the 2D structure of graphene oxide, that it can volumetrically disrupt as much as possible. So here we have disruption of polymer chain packing and then the reorientation of water channels, because that is what we wanted to do with facilitated transport membranes. And you also have an enhanced solubility of CO2. But on the other hand, you have graphene oxide, which is a barrier property, which still retains a barrier property and leads to longer diffusional pathways for CO2. And on the porous graphene oxide, you have this unselective pores, which is going to help us with the fight against the barrier property. And that's the reason why you increase the permeance quite a lot. However, there is a lower diffusional resistance, and that's the reason why you decrease the selectivity a bit. GOPG, on the other hand, it still retains the barrier property from the graphene oxide, but then there was, this is a typical classical case of enhanced interface compatibility, which leads to a rigidified interface where you lower the permeance quite a lot, but then increase the selectivity. But the increase in selectivity was not evident at 0.28%, but it was evident at higher loading of GOPG, where we are able to increase the selectivity of the system by up to 80 or 90 separation factor of CO2 over nitrogen. And in this system, we also found that it is only 0.28% of graphene oxide that is necessary to disrupt the polymer chain to our benefits. And that low disruption or low loading is mainly because of the two-dimensional structure and the volumetric effect that the graphene oxide has on the disruption of 2D on the polymer matrix itself. So we subject this 0.28% loaded graphene oxide to a condition where we wanted to test it about the durability of CO2. So what we did is that we stored the membrane for about 1.5 years and then checked about the CO2 permeance and selectivity. Usual polymeric membranes tends to have reduced performance due to chain relaxation of the polymers, which is very natural when it's not operating. But then when we added this porous graphene oxide, these 2D materials helped in slowing down the chain relaxation. We only obtained up to 12% reduction in CO2 permeance, while on the neat neat polymer membrane, we reduced the CO2 permeance by as much as 25%. So in conclusion about this study, that 2D materials are very good in as nanofillers to be dispersed in facilitated transport membranes. And given the extremely thin nature of graphene oxide on one dimension, the defect-free selective layers, which is less than 200 nanometers, and one in-plane alignment of GO, where we were able to do it with respect to this hybrid facilitated transport membranes to be cast as thin film composite. And the CO2 permeance and the selectivity, we were able to reach very optimal numbers with just 0.28% of porous graphene oxide. In this case, we have the assessment where it says that the performance is quite nice, the stability of the membranes, because we tested up to 1.5 years, which was very good. And the processability of the membrane is also good because we were able to coat 200 nanometer selective layer. That is what is needed for this application. But how about upscalability? Of course, we can upscale bar coating membrane fabrication process, which is going to make us flat sheet modules. But we are traditionally hollow fiber membrane people, so which means that we wanted to see if we can do the same system in hollow fibers. But then we have to remember that 2D materials on a hollow fiber, which is a curved structure, is a challenging mechanism. So what we tried that is to see if the lateral dimensions of the graphene oxide changes any of these properties. So what we tried here is that we wanted to choose different lateral dimensions of graphene oxide to see if they can change the effect of graphene oxide or of the dispersion in the polymeric membrane to get better CO2 permeance and the selectivity. So we used a very, very normal method with ultrasonic fragmentation. With that amount of fragmentation time, we were able to control the size of the graphene oxide flakes that were dispersed. So basically, when you increase the sonication time, you have a reduced lateral dimensions of the graphene oxide. And we also made them porous, which is the same procedure we described before, that with these 3 dimensions, we were able to get 3 different porous graphene oxide, which was of different lateral dimensions. So we fabricated them into hollow fibers. And in here, we used a different coating mechanism, which is dip coating. And we were able to achieve the same in-plane alignment of graphene oxide in this system as well. And the reason is because it's not with the surface energy that we spoke about in the mechanically forced alignment in the flat sheet. Here it is because of the shear alignment. When we dip coat the nanocellulose, the graphene oxide platelets orient themselves towards the surface so that they can have shear alignment and it still retains this in-plane alignment of graphene oxide. So when we have a low concentration of the gas solution, we were able to coat the thin layer up to 190 or 200 nanometers in thickness with respect to the porous support on the top of the porous support. So what happens when you have a graphene oxide which is of different lateral dimensions? Increasing lateral dimensions will have disrupt the polymer chains even more. That is good. But then water change channels is also reorient. That is also good. But then the gas diffusion reduces, and the barrier properties of the graphene oxide itself is going to affect. So that's why there is an optimal lateral dimension, where these 2 pros and cons are optimized. And that was something around, we call it as PGO6 or the graphene oxide 6. So we did not stop with there. We want to increase the system even better. So what we used is that we used mobile carriers, which are basically small molecules that have high affinity towards CO2. And in this case, we took an amino acid, an ionic liquid, and 2 amino acid salts and 1 ionic liquid. And we found out that the species which are forming carbene or carbonate adducts are much better with respect to performances than the ones which are not forming the other one, which is carbonate species. So we expose this system also to CO2 methane studies, where we are increasing the CO2 concentration on the feed side to 40%, and also increasing the pressure from 0 bar or 1 bar to up to 20 bar on the feed side to see if it has any effect. The addition of nanofillers is definitely proving positive because the mechanical strength of these membranes were quite stable until 20 bar of upstream pressure. And the water retention on this high pressure was also relatively good thanks to this hydrophilic nature of graphene oxide. But what exactly helped, like for example, when we look at this figure, what is the actual role of mobile carriers here? The mobile carriers is basically used to increase the CO2 solubility in the matrix and also diffusivity because of the mobile nature. But in here, they also help with the phenomenon called carrier saturation resistance. Facilitated transport membranes, when you increase the pressure on the feed side with respect to CO2 partial pressure, then you saturate the carriers that is present in the polymer matrix eventually, after which the facilitated transport never slows down, the mechanism slows down. But when you use the mobile carriers, we see that the resistance to this carrier saturation phenomena is much higher in these mobile carrier systems than the systems which are not using mobile carriers. So with this, we have facilitated transport membranes, which contains this macros. We have included hybrid facilitated transport membranes, which includes graphene oxide and porous graphene oxide, which increase the performance. On the other hand, we also use mobile carriers to further improve the performances. And in this case, we reached up to a CO2 permeance of 825 GPU with a CO2 nitrogen selectivity of 30 and CO2 methane selectivity of 20. And this CO2 methane selectivity was also retained at high pressure, meaning that in our assessment, we have the performance, which is a positive side. Stability was also good. Processability and upscalability was also very good. So eventually, we scaled up these membranes into pre-pilot modules, which is of sizes up to 200 centimeters squares. We also made a module which is up to 2,000 centimeters squares. So we choose three different membranes. One is one with just the porous graphene oxide inside, and the other one is with porous graphene oxide with mobile carriers, two different types. One is amino acid based, and the other one is ionic liquid based. So these membranes were then shipped to test in two facilities. One is the Kola Semi-Industrial facility, where I was there testing these membranes in the slipstream of cement industry. And we also sent these membranes to the Advanced Capture facility in the UK for testing for impurities. So in the field, we found out that the membranes perform quite well. The upscale membrane modules perform quite well, where the CO2 flux was a function of water activity, which was quite evident because of the facilitated transport membranes. And the purity was up to 50 to 55% at the conditions that we tested. That was quite expected of the membranes in single stage operation. And we also found that the mobile carriers increased the permeance and lowered purity a bit. So the performance, on the other hand, what we obtained at industrial scale was much better with respect to the lab scale. When you look at the permeances, it was quite high. The CO2 purity was also about in the range of 50%. The reason why we get this very high performance or increased performance with respect to the lab scale performance of these modules is because we use vacuum on the permeate side because of the good area, high membrane surface area. So use of vacuum is justified, which increases also the pressure ratio, and high temperature of the flue gas, which was around like 80 degrees to 90 degrees. And also because the water profile in these systems are much more predictable and reliant. And that's the reason why we were able to record very good performances in the field than in the lab scale. So we also subject these materials to 14-day testing without any disturbance. So a continuous exposure to the flue gas. Please note that these flue gas was not treated, which means they are raw flue gas with impurities present in it. And when this was exposed for 14-day operation, there was no drop in CO2 flux or the permeability or the purity, and it was recorded to be quite stable. The performance from the SOx and NOx exposure also showed that when we expose it to SOx and NOx with a very high concentration, we never saw a drop in performance of CO2 purity. So with this, we saw that these membranes, which are hollow fibers modules of facilitated transport membranes, they were tested in real flue gas. And the CO2 permeance in the testing site was actually 1.5 to 1.9 times or double that respective of the laboratory scale test. And that reason is because of the high good conditions at the industrial scale testing. And we also proved that the membranes are good for impurities and also have long-term stable operation. So now that the membranes have been validated, we got the data from the validated membranes, and we wanted to use that as a basis for our simulation study to design a membrane system with 2 stages to reach the targets of CO2 purity and recovery in typically. So for this, we use two different cascades. One is with 2-stage without recycle stream, and the other one is 2-stage with recycle stream. And the CO2 and the flux, the components of CO2, nitrogen, and oxygen, which is the gas composition of the flue gas, was mimicked to that of the case in coal seam cement industry. And the basis was set to a pilot scale, which is 50 normalized meter cube of flue gas. This is going as a feed. For this system, we also chose 3 different membranes. One was the membranes which contains porous graphene oxide and the mobile carrier, which is of high permeance. Second one was the membranes with high permeance as well, with porous graphene oxide. Both of them have very high permeances and lower selectivity with respect to the third membrane, which we chose, which is fixed site carrier that was developed earlier in the group of N10U, which contains polyvinylamine, and that has a very high selectivity, but on the other hand, very low permeance. So what we want to do is we want to mix and match these membranes to see if they can, the positioning of the membranes actually make a difference in the performance of the 2-stage system. So in this case, we evaluated 4 different cases. What is case A, where you have both membranes of lower permeance and high selectivity, and case B, which is of a high permeance and a high medium permeance or high permeance. Both are relatively high permeance membranes and low selectivity. In case C, you have high permeance membranes on the first stage and a high selectivity and low permeance membranes on the second stage. And in case D, you have the opposite, where you have the case C and D, you have relatively high permeances on the first stage and lower selectivity or lower permeance on the second stage. So what happens with 2-stage process without recycle? So the targets that we set for this kind of system is that we want to reach a recovery of about 80 to 95% and a CO2 purity of at least 95% for the storage applications. So we were able to see that the maximum CO2 purity that we can obtain is a function of interstage compression, which means that we have to compress the second stage because of the absence of recycle stream to get a CO2 purity that is in the range of over 95%. And even in this case, we were limited to achieve only about 90% CO2 purity in this system for both all the cases A, B, C, and D. The empty shapes show you the recovery of 80%, and then the fill shapes show the recovery of show the systems with the recovery of 90%. So with 90%, with the higher recovery, you also decrease the CO2 purity that you can get at the second stage. So clearly, the 2-stage process without recycle is not a system that we would go for if you want both recovery and purity to be high. So in that case, we go to something which is expected, which is the 2-stage process with the recycle, or we eventually go to a 3-stage process. But we want to limit the study to 2 stages to keep it as simple as possible. So we chose a recycle stream that goes from the retentive side back to the feed side of the first stage. And in this case, we have the recycle ratio, which is the amount of recycle that is present with respect to the feed. That is obviously one of the deciding parameters of how good the system is. And we wanted to see how it changes with respect to the positioning of the membranes. So in here, we saw that the recycle ratio was much, much lower for cases C and D for getting a purity of more than 95%. For example, if you look at this area here, say that the potential for case A is much better than case B and C and D in this region. But if you go to a higher recycle ratio, then you get that the case C and case B is much better. Case C and D are much better. So with respect to the recycle ratio itself, you want it to operate at lower recycle ratio. In this case, you don't want the membranes to be of the same type in both the sides. You want the membrane to be highly permeable on the first stage and highly selective on the second stage to operate at a lower recycle ratio. So what happens with the energy requirement? How does it change with the positioning of the membranes? Here we also saw a similar trend where cases C and D, which has a very high permeable membrane on the first stage, and low permeable but high selective membrane on the second stage, was much better with respect to the purity of more than 90%, and it has lower energy consumption with respect to the case B, which is the highest, and case A, which has both high selective membranes on both the stages. So in here, we draw a same conclusion that C and D requires less energy for CO2 purity, more than 95%, which means that you need a membrane which is of high permeability in the first stage and high selectivity in the second stage. But what happens to the membrane positioning? Where does it change about the membrane area as well? Yes, it does. And here we have a very interesting trend where, for example, case C and D, if you look at the trend of CO2 purity and the total membrane area required, it reduces and then increases. But then there is a place where there is a minima where the membrane area requirement is actually reduced to an extent where it's the lowest in that system. So which means that something is happening in the system of case C and D where the membranes are different in both the stages. Case A is having a high selectivity membrane in both the stages, and case B is having high permeance membranes in both the stages. So that's the reason why they follow a simple trend. But when you mix match the membrane, you have a trend which is compensating each other. So we wanted to look into detail what actually has happened in the system. So what we did is that we checked the exit concentration that is going into the permeate, which is the purity of the second stage, which is basically the outlet CO2 concentration of the second stage. And we wanted to see how the first stage has purified the CO2, which means this on the x-axis, on the y-axis, you see is the feed CO2 concentration that goes into the second stage, which is basically the permeate CO2 concentration of the first stage. So here, when you have a membrane of very high selectivity on the first stage, then you have higher CO2 concentration, which is the case A. So in the sense that when you have a case A, you have a higher CO2 concentration, which means that the membrane on the second stage is forced to operate at a higher CO2 concentration than in the case where you're doing a membrane with of a high permeance but a lower selectivity. So which means the feed concentration of CO2 to stage 2 obtained from stage 1 inflicts large penalties. So which means that you don't want a high selectivity membrane in the first stage because you want a low selectivity and high permeance membranes in the first stage, so that there is a bulk purification of the flue gas, so that there is no penalty of the second stage, which means the second stage operates at a much lower average of the driving force. So here we have shown that a two-stage cascade with and without recycle can be used with for purifying CO2 and reaching a target of CO2 purity up to 95. So CO2 purity over 95% at the same time the recovery of 90%. And in this case, we also have proved that the positioning of membranes of different properties in the different stages is very important and can influence the performance of the system significantly. High permeable membranes, which are low selective membranes, which is in the first stage, when coupled with high selectivity, is actually required to be is actually proven to be the best system under these conditions. But it has to be noted that this is very dependent on the CO2 purity and the recovery that we are targeting. It can be very different on different applications that we are looking at. So with this, I have tried to re-summarize how the membrane journey is and what we have done so far. So looking at the same picture again from the previous slides, we saw that we have had the membrane idea, and then we have developed the self-standing films with respect to a couple of the membranes. We also developed flat sheet, we developed hollow fibers, and we also validated them in the pre-pilot scale in the cement industry. And with the validated data, we also did feasibility studies as opposed to many feasibility studies that work on self-standing films data or probably membrane data from flat sheet membranes. It has to be very well noted that this data from the industrial modules are very different from the data from the membranes in the lab scale. So when we look at the journey, in my PhD, we have gone across this far thanks to, again, the excellent consortium that I was working with and the help of the people that was in the consortium, making it very fast-tracked for the membrane development. Currently, this membrane has already been patented and it is licensed to a company called Aqualung, which is now carrying out the commercialization of the membrane and also taking up the pilot scale demonstration very soon in a company in the US. For more details on the pilot demonstration, you could obviously go and visit their website, which is aqualungcc.com. And they have plans on testing the membrane in a large-scale facility And recently, the Research Council of Norway also granted a huge sum of money to commercialize this membranes into pilot modules for the development of the membranes further. With this, I would like to thank you for this opportunity for presenting in this European Membrane Society webinar. I would also like to thank all of the people that was involved in my PhD study, and also the European Membrane Society for the several travel and grant and poster awards, and also the biggest honor that I've gotten so far is this Patrick Beers Prize for the best PhD in membrane science. And so thank you so much. I will be open for questions now.
Thank you very much for your presentation, Dr. Janakiram. A very interesting presentation about the last slide is really the point of research going to industrialization. It takes a lot of time, a lot of energy, passion, and it is not a straight line. It is made also by junctions, by deviations, and it takes really passion to hold on throughout not days, not months, but years of research to get to the point where you went, and hopefully you will continue. Arriving to this point, I will not say that you are going to surrender. So indeed, that you are going to continue this wonderful work on this topic. Okay, let's go to the podcast-like part of our webinar, meaning that the paper is open for discussion. You can write your questions in the chat of the YouTube channel, and so I will be able to propose your questions to our speaker. I don't know if some question in the meantime arises. And nevertheless, I have a question by my own, and it's concerning future work. No, so you arrive at a very good point, and so industrialization indeed is ahead. Are you thinking to go to industrialize your membranes, or it is only specific to this application, in your opinion?
You mean industrialize for different applications or for post combustion?
I mean that you're going to commercialize your product, because earlier you have made a development of a product, and a very interesting one. So I think that it might be of interest also to other companies. No,
Yeah.
if you have
So
thought
there is
about
this.
this, or if it is a standalone application, let's say.
Yeah, so this company Aqualung, which has taken about the task of commercialization. They work in closely with NTNU right now, and also with me sometimes. That they are taking up the commercialization to produce modules of industrial scale and test them at conditions for more longer time, prolonged time, to get the pilot data. At the same time, looking at the other clients where this can be applied as well.
Okay. Thank you. And a more technical question.
Yeah.
Does nanocellulose pose some limit to your application, since it is known that cellulose is somehow delicate substance, no, concerning pH values, concerning temperature, and concerning also the behavior of mechanical strength. So, in respect to other bulks making the membrane, I think that perhaps, and I'm asking about this, your product needs more care.
On the cellulose, yes. But the other thing that has to be noted is that, okay, the first part is mainly cellulose as a polymer matrix itself. In that case, yes, it will be very difficult. But that's one of the reasons why we also said that it's a very interesting phenomena that happens, but not really something that we would look for post-combustion capture. But on the second case, where you're dispersing nanocellulose on a polymer, it is actually already dispersed, which means that it's solidified and it's the polymer, which is the maximum component of the matrix, not the cellulose anymore. So in that case, of course, until the manufacturing point, it is playing a quite delicate role in the sense that you have to take care of nanocellulose as much as possible. But then nanocellulose is one of the toughest material. Like if you look at gas permeation, for example, cellulose acid, it has been used for it's a workhorse of gas separation for a long time. So technically, it is quite a good, interesting material for gas separation as such. And nanocellulose is because you basically have cellulose with a confined dimension right now, which is in one dimension. It's a nanoparticle. So you have very interesting use of the celluloses. But of course, since the manufacturing of the celluloses is already a very difficult process, because nanocelluloses is done by this acid hydrolysis and all those processes where you get the structures which are very different, and the surface properties are very different with respect to each manufacturer. You will have challenges basically with respect to the manufacturing part. But then when you optimize the system to a particular system, it is very interesting in the sense that it can retain its one-dimensional property, and now you're replacing the polymer with let's say 40% of the material which is bio-sourced, so which is giving its own advantage, for example. And then the one dimension, if it's preserved, then it brings its own properties.
Thank you. Okay, we have a question from the audience. Clara is thanking you for your presentation, making her congratulations to you. And she's asking if synergic properties of EL and GO in the MMM layer, if you are using them together.
Yep, we did use both the graphene oxide and ionic liquid together in a single layer, and that was something that we did it here, for example. Can show you a bit more there. Yeah, probably you see a different one. So let me see here. So what we did is that we have this. All right, I think I have messed up the system a bit. Yeah, I can show it here already. So you have a system where ionic liquid was used as a mobile carrier, because ionic liquid as such is a small molecule, so which means that you can use that as a mobile carrier. So we know that it's compatible with the system, which means that in this case, we added just the ionic liquid on the polymer, and we found out that this EMM acetate has actually given us good performances at 10% loading. So for each system of mobile carriers, it was a different optimum that was obtained because of the properties of the mobile carriers, properties of the interaction between the polymer matrix and the mobile carrier, and so much, like, for example, the solubility of the mobile carrier. So for this case, we found out that 10%, it was quite interesting that we can add only 10% of the ionic liquid, and it was already helping us. So we did use the same 10% concentration with respect to graphene oxide as well, because we know that both of them are hydrophilic, so both of them should be compatible with each other. And it was actually compatible, as you mentioned in your question, that it was synergistic effect, where we had this porous graphene oxide, which took care of the mechanical properties and also helped with the water uptake, for example, or the polymer chain disruption. And then you have the mobile carrier, which is basically helping you at high temperature for extra permeance. And that's what we actually saw in the system, where here I've written that the EMM acetate, for example, the reason why we have written this, I did not highlight this, of course, in the presentation because I did not have time. But then if you look at it at 35 degrees Celsius, you have the viscosity of the ionic liquids to be 74, which is quite high. It's quite viscous. But then at high temperature, they become really less viscous, so which means they become more mobile. So that's one of the reasons why we are adding these mobile carriers, because we want them to be more mobile at high temperatures so that you get the maximum CO2 out of the system. And that's why we have an increased performance up to 1,400 GPU when the actual membranes in the lab was only up to 730 GPU. So yes, the synergistic approach is still there. And the porous graphene oxide on this side is because when you have so much of this system which is dilute, the mechanical reinforcement is very necessary. And that's where the graphene oxide comes in, because they don't really change with high temperature.
Thank you. Claudia Ruiz asking if the positioning of the two different membranes have been already tested at lab and or at industrial scale.
Yep, thank you for the question. So yes, this was a feasibility test, which means that we haven't done it in the industry, no. But what we have done in this current feasibility test is that usually when we look at feasibility tests in membranes, people, I mean, not everybody, but then many people try to use or tend to use the data from the lab, and that's normally okay because since we had this data from the industries already, what we did is that we did not take the material performance, but we take the module performance of the membranes. So this feasibility test that you see on both the stages, we have used module performances because this membrane that you have in the first stage, or the like two different types of membranes, these two membranes were the ones that was discussed in this webinar, and the third membrane, which was already licensed to Air Products before from NTNU, so that was already tested in cement industries as well. So we had the industrial data of the performance of these membranes. So we used that performance to simulate these cases, but we never put them together because this is of a different generation, basically. So it was a couple of, at least 5 years before, I guess. So this was very recent. So one way is to look at both of them, but the other way is that we were only able to scale up only a couple of membranes. But when you look at the actual performance of different membranes with this recipe, we can actually tune the selectivity and permeance to whatever extent we like based on the components compositions. So in that case, we have a possibility that we can also make a membrane which is highly selective from the system.
Thank you. Clara again, she's wondering if a cost estimation of a membrane fabrication with a high level of percentage ionic liquid in the membrane you have shown previously was performed, and how did this affect?
Yeah, so this was also a very interesting question. Thank you so much. And something that we have thought about, and something we also know that we are at an advantage here. The main reason is because during the EU project, and thanks to Akin has said, like a very wonderful consortium we had this estimation of cost of materials that we will come into raw materials to see if this work will be kind of like, it's making sense from a material manufacturing perspective. And in that case, what I wanted to say is that we have a solution which is very, very lean, and we are making a system where it is 192 or 200 nanometers, so which is basically very less polymer. And in that polymer, you have 10% of ionic liquids, so weight percent of ionic liquids. And when you compare the graphene oxide, it's 0.2 weight percent. So technically, the most expensive components of this system is graphene oxide and ionic liquid, if you think about it. And that's 10% and 0.2%. And the amount of polymers that you need for 200 nanometer film is very, very less. So which means that you can make huge amounts of modules with very less money. So from a design perspective, it makes sense to have. So that's one of the reasons again for the ionic liquid plus nanocellulose study, because that had up to 40% of ionic liquids. Then you really need a lot. And the membranes were very thick, which is 2 microns. So that's a lot of material. So all these things also come into play because when we make post-combustion capture membranes, we also have to think about the processability from the perspective of raw material use as well. And that's taken care of, and it's not proving to be that expensive, if that answers your question.
Thank you. We have a last question from Lidietta Giorno. Thank you for the nice presentation. Can you comment on the membrane stability in case of membranes with mobile carriers? Thank you.
Yeah. Thank you so much for the question. Very good comment that it's quite expected that when you have small molecules of CO2 affinity, you can intend or you can expect that they go really bad, or they are the ones that are very much prone to unstable conditions, for example. So what we did is that we wanted to test, basically we wanted to do the bad postmortem test where we exposed the best or like the worst, most vulnerable system to the worst possible conditions. So what we did is that to the Sheffield study, we actually sent the membrane modules which has mobile carriers, not the membranes without mobile carriers. So the graphs that you see on the right are basically membranes which are having mobile carriers. In this case, it's ionic liquid, the first two graphs. And the second one is proline K, which is the mobile carrier, which is amino acid based. So the worst condition that can happen, affect the mobile carriers is the acidic components, which is SOx and NOx, because they are very, they are reactive because of the small size. And they also tend to react faster with the SOx and NOx. So we expose them with to as much SOx and NOx as possible. For example, this graph you see 400 ppm of SOx, 400 ppm of NOx, and here you have 1500 ppm of SOx. So when we expose this, and we did this accelerated aging study, which is basically the membrane going bad with respect to conditions of instability, and we found out that mobile carriers really did not play a big role there. One of the possible explanations is because of the hydration, because you have mobile carriers which are hydrated right now, so they are the acidic components are much more permeable than the CO2. So which means that you always ended up getting the NOx on the other side, but the CO2 flux did not change, the CO2 purity did not change. So that is what is important, because when the NOx or SOx irreversibly reacts with the mobile carriers or the carriers present in the membranes, then you will see an eventual drop in the CO2 purity, because now the carriers don't have effect of CO2 transport. But that we did not see. We saw that the CO2 purity was very stable.
Okay, thank you very much. And waiting for eventually last second questions. I don't know if there are other. No, there is another question. Clara again, another curiosity is the last step of scale up, where you rely on convincing industrials and such, and which barriers did you find in performing this action?
Yeah, that's a very interesting question. Of course, this is something that is expected out of a system that is going to commercialize. So, which means that you have a lot of hurdles when it comes to industries. One thing that I'm happy about is that within the EU project, there was very good consortium of industries which made it fast track. And now that we have Aqualung on board, they are very good. We are given the membranes in safe hands, in the sense that they have taken care of all these hurdles, and they are proving to be very efficient. So, which means that they are officially taking care of these hurdles with some of we trying to help as much as possible. Yes, these hurdles are real, and that is being taken care of by the external company.
Okay, thank you. If I may add personally something, I think that it is important also to build up the confidence in the technology. It was a main problem of membranes some decades ago, where we had some problems of confidence due to over design, due to excessive fouling of the membranes, to industrial application failures. And I'm very happy to see that in the last decades, all the researchers on and membrane technology actors have put a lot of effort in increasing the confidence of this technology again, qualifying again membrane technologies as best available technique throughout many different applications, wide broad applications. So that indeed in the last decades we have really performed a wonderful work on this topic to come nearer to industry and to build up again confidence with industry again. I don't know if there are another question waiting for. In case another question, I want to advertise for the next webinar, so that indeed we have the next webinar on May 4th, again at 4 o'clock chat, about the Open Membrane Database, which is an action promoted by some membrane actors concerning the formation of an open access user-sourced archive of water purification and desalination membranes and related data to this. So it appears to be an interesting action, and it will be presented in the next webinar next month. So I don't know if there are other questions, probably guess not, so that indeed I want to thank the active audience of today of this webinar. So thank you very much joining us here and to follow our speaker, Saravanan Janakiram, which we cheer with gratitude. And good luck for and best wishes for your past work, but especially for your future work, which appears to be very interesting and promising. So we expect to hear from you more and very soon. So thank you very much to audience and speaker. Thank you. Thanks goes also to Elena Tocci, who was in the background, mastering very well the technical issues of building up a webinar. And have a nice evening, and stay safe. See you soon. Thank you.
Bye-bye.
Goodbye.